what I found was there was a lot of despair around climate change and how do we resolve the problem. And one of the things I found with the work I'd done in renewable energy was my own despair had really dissipated in terms of being able to solve the problem from the sort of energy supply side. For sure, the policy stuff is big. So what I'm going to talk about today is basically, what you can do individually and what we need to do as a province and how electrification is really where we're going. So I feel like in the last year, there's just been incredible momentum building around the world, really. And of course, Greta is a big part of that, but obviously thousands of other people too. So, these are some of the things that I feel we need to be optimistic about in terms of being able to move forward and address climate change. And did anyone hear Mark Carney on Enright a week ago? Okay, so about a third of you or a quarter of you. I'll just let you read this quote from what he spoke about last week. And I think, that's going to become more and more apparent, and he's leaving the Bank of Governors position and taking up the position with the UN. He'll be one of the key people at the Conference of the Parties in Glasgow in the fall. So, I hope that that's also a sign of, progress, as we've got a guy like him working with the UN on climate change. Yes, he's a capitalist for sure, but I also think he has a very good sense of where companies need to go, and he's very interested in creating a structure that pushes them to look at net zero issues. Okay, so what do I want you to come out? This is something I learned with Gord in our program planning in the India project. What are the outcomes? So here are some outcomes I hope you walk away with today. One is that you believe that an 80-90% reduction is possible in Ontario. The other is that I hope many of you are already advocates for addressing climate change, but I hope those of you that need a little more motivation, or those of you that are already in it, remain motivated, that you're an advocate and hopefully an adopter of the changes you can afford. And affordability was also brought up in the questions before I started, so that's a big issue. So we're going to look at greenhouse gases, and then the province. So that just in case I've got GHG a lot in this presentation. Let's make sure nobody misses that. And if it's just a little fuzzy in your brains, the physics, it really, it's obviously very complicated to model, but the molecules in the air that reflect infrared heat back to the Earth are basically water vapor, CO2, plus some other gases. The other gases are significant, but usually when we talk about climate change, we talk about CO2, and in terms of the numbers and the ratios, we talk about CO2 equivalents. So it's as if those other gases were CO2. So we're going to, when I talk about CO2, it's looking at the big picture of all the gases that reflect radiation. There's 6 of them under the UN IPCC sort of technical guidance. Okay. Gord had a slightly different number, but the IPCC report that came out over a year ago basically was saying then for 1.5 degrees, we need a 45% reduction by 2030 globally, and 100% by 2050. So those are the broad numbers we're working with. And I don't particularly get uptight if it's a few percentage points this way or that way. This is not a bullseye we're aiming for. We just want to get somewhere towards the bullseye. But that's certainly the realm that we're looking at. A couple of other numbers. Just gigatons are how we usually talk about lots of carbon at the global level, because the world produces about 54 gigatons of CO2 equivalent. That's the little e there, which includes the other gases. We're about 720 in Canada right now, about 0.7 gigatons and 720 million tons of emissions. And then Ontario, 2017 is the last set of numbers, we're at 159 megatons. So just to sort of frame the scale and the scope of the emissions. And this is a lot of information, but the key thing here, this is for the world, there's the 54 gigatons of carbon dioxide equivalent up here. And it's broken down into the different sources. So this big blue here is CO2 from burning fossil fuels, okay? So it's a big chunk of it. And then you've got methane, which leaks out and is created by a variety of sources. Methane related to energy production, methane from agriculture, methane from waste disposal. So that's our organics, in our landfills, anaerobically digesting. So these three are the methane contributions. Methane is a very powerful greenhouse gas. Many of you probably know that. And then we've got the nitrous oxide. It's laughing gas, but not so funny in this case. And there's the nitrous oxide contribution, again expressed as equivalent of CO2. It's actually much, much smaller because it's, I think, 210 times more capable of reflecting radiation than CO2. So, but many of these nitrogen oxides are created by burning of fossil fuels. So these are basically the result of burning fossil fuels. If we burned no fossil fuels, everything would disappear except for this waste number and probably some of the agriculture. All the red, two of the greens, all the blues would disappear. Then we'd be left with these F gases, which are refrigerants and some other industrial gases. So they're a relatively small contribution. And then we've got man-made land use and land use change forestry, which is forest fires caused by man, not natural forest fires, although that starts to get tricky when you look at Australia. So you can see, anyway, that's the forestry part. That's mostly cutting and slash burning of land for agricultural purposes. Okay, so that's where the 54 billion tons comes from. And my focus has always been on the fossil fuel component because it's such a huge part. And if we want to look at, who's responsible for what, this is a little bit different number here. They've taken out the forestry numbers and the and the nitrous oxide and the methane, but in relative proportion they remain the same. And if this whole block is the worldwide emissions, the US is this area, we're in here. It actually says 573 million tons, but that's because it doesn't include the forestry and some of the other stuff. China's big, of course, and has doubled in the last 15, 20 years roughly. But really, there's no magic bullet. Even if all the emissions from China disappeared tomorrow, we still got a problem. So everybody's, got to contribute. Maybe there's a few countries down in here which are sort of insignificant if they don't make a lot of changes. But there's 100 countries that have to change substantially for us to make progress. So it does need to be a coordinated global effort. So let's look at Ontario more specifically. The current government's goal is that we would be 30% below our 2005 emissions by 2030. So the 2005 emissions were 204. The current government messed around with the numbers a bit, and the current goals aren't nearly as aggressive or ambitious as the previous Ontario government. So in fact, the way the numbers were adjusted, our goal for 2030 is 142, and we're actually already at 159. So it's not a very ambitious goal. It's not that it's easy, because it still requires significant changes. And we made a lot of our gains from 204 to 142 by closing the coal-fired generation in Ontario. That was like 30 megatons. So now we're down to buildings and cars and other stuff that we've got to start addressing. Okay, so those are the goals for Ontario. So if we look at the emissions in Ontario, though, we see there really isn't any particular thing we can do that takes out a giant chunk. So I'm going to show you a pie chart. It's ugly. You will not have to memorize any of it, but I think it's important to look at the relative proportions. And I'll just mention now, because it's such a large group, I think we'll just hold questions till the end, and I'm sure there'll be lots of questions and comments, but we'll just hold them till the end. So if we look at Ontario, and this is the 159 megatons from 2017, which is the latest official numbers. This is from the report that goes to the United Nations. We can see that this big blue chunk is passenger vehicles, about 34 million tons. Then we've got freight trucks, rail, and aviation, about 18 million tons. We've got recreational vehicles, about 4. We've got heavy industry, so a lot of this would be coal and natural gas, energy consumption in heavy industry, and some fuel oil, but less so than the oil being used for this. You'll notice that electricity in Ontario, production of electricity, is only 2 megatons, and that's the natural gas that's used in our peaking plants. So it's actually a very small contribution to Ontario is from production of electricity. And then we've got buildings. So this is heating. Air conditioning isn't particularly greenhouse gas intensive because it's been made with electricity in Ontario, which is actually very low greenhouse gas. So most of this big building chunk is the heating of buildings. The vast, probably 98% of that is the heating of buildings. And although many of us live rurally and may use, wood or propane, the bulk of this is natural gas consumption, because that's how most of the heating's done for the millions of homes in Ontario that are near bigger urban centers, and all our institutional buildings, and our commercial buildings, and our malls, and our office towers in downtown Toronto. All this is the natural gas associated with operating those buildings. Then we've got agriculture, which includes the fuel for agriculture, crop production, and animal emissions. Then we've got waste from our landfills, where we've got organics decomposing, light manufacturing. This one's sort of interesting. This is oil and gas production. I believe that most of this would be Sarnia. So it's related. So when we start reducing these big ones here, building heating, but especially passenger transportation, we start using less oil or gasoline and diesel, you also impact the upstream. And that's one of the things about these kind of charts is it doesn't include these numbers don't include the emissions for gasoline that we might be buying that was processed in another part of the country. So that's not in here. The upstream, these are point of use emissions. So if we reduce all these by doing some good stuff, we also reduce emissions elsewhere in the country, which is important to consider. Okay, so let's look at personal stuff. If we just want to sort of ratio it, worldwide, we produce about 20 tons of greenhouse gas per person, roughly. And in the world, it's about 7. So this is a reflection of our more energy-intensive lifestyle. Yes, we do have to heat our buildings, but this is a reflection of the more energy-intensive lifestyle. If we look at Ontario, we see that we're actually only about 11.3 tons per capita compared to the 20 in Canada. And quite a lot of that has to do with the fact that our electricity is very, very low carbon in Ontario. I try not to say clean because a good part of it is nuclear, and we do have waste fuel from that. But a good part of our electricity is made with low greenhouse gas emissions. So we're actually lower than the Canadian average. So about 11.3 tons. So just try to remember that number as we talk about activities you can do. 11 tons is what we are per capita and the broad averaging. And obviously, depending how many people live in your house and how many people you carry in your car and all sorts of other things make that vary. But let's just take a look at the choices that produce those emissions. So we got to get around. We use lots of different machines, bicycles sometimes, maybe, canoes, who knows. We've got to heat our homes. We've got a bunch of different energy sources we use to heat our homes, which have different greenhouse gas impacts. We can choose food in a variety of ways, vegan, vegetarian. Whether we purchase it locally or not makes a difference. And then recreation. So pretty much obviously for recreation, unless you're driving a motorboat an awful lot, flying would be your biggest emissions. If you've flown anywhere a long way, it has significant emissions. So let's look at what's attached to these activities. So ICE is internal combustion engine. So a piston engine burning gasoline typically. If it's a very efficient hybrid car and you drive about 20,000 kilometers a year, you're probably at about 2 tons. If you drive a V8 pickup truck, the same distance per year, you're at about 8 tons. So remember, 11 is the average in Ontario. If you heat your house with natural gas, and it's a modest size, relatively efficient house, you're probably around 4 tons. I'm not talking, passive solar, net zero homes. I'm talking the average smaller home that would be in Toronto or London or wherever. I realize none of us are on natural gas. Anybody on natural gas here? Maybe a few people. Okay, quite a few. So around 4, and then if you got a larger house, maybe it's not so efficient, around 10, even on natural gas. And if you go to propane or oil, these numbers go up substantially because there's a lot more carbon per unit of energy in propane and oil. And if you're burning wood, then you're into the debate of where did your wood come from, and if it's from your own wood lot, and it was just going to rot in the forest, you probably have a neutral contribution. If you're buying it from somewhere that's being turned into a parking lot, that's another equation we're going to have to look at. But you know, the bulk of emissions in Ontario is not from people living rurally. Cost for propane and oil is an issue, but the emissions are coming from, you know, the millions of people who have natural gas heated homes and all their commercial and institutional buildings. That's the bulk of the heating greenhouse gas contribution. These are very rough numbers, but from my own reading and research, it's around 2 tons if you just sort of eat everything, and probably around 1 ton if you eat vegetarian, and you have sort of a normal adult diet. But obviously that varies a lot by individual. So it's just to put it in perspective that if you're an omnivore, it's sort of like driving a hybrid car. I want to think of it that way. If you're vegetarian, it's sort of like driving a hybrid car 10,000 kilometers a year. And then the last thing is, I'm going to put here is flying. And 1 Toronto-Paris return trip is about 2 tons of greenhouse gases. So it's like driving a hybrid car all year. 1 return ticket to Europe, roughly. And that's because airplanes carry about 100 to 300,000 liters of fuel to get you where you're going. And that's because they go really fast and you get there quickly, but it takes a lot of energy to do that. There's no simple solution for more efficient aircraft at the moment. They could run on biofuels potentially, but that has yet to be fully commercialized. So if you lived like this, and we're not including how many people live in your house, but roughly these would, on the low end, be about 10 tons, and on the high end, about 22 tons. Remember, the average in Ontario is about 11. And we want to take this down, you know, by 2030, we want to take half that out. By 2050, we want to take, you know, 90% plus out. So we got to get down in the range of 1 ton or less per person to make the dent we need to make in emissions. Okay, so how do we reduce emissions? Well, we can just buy more efficient stuff. Cars, Gord mentioned, we've already sort of done the light bulb thing. Many of us probably have programmable thermostats. So, you know, that gets us part of the way there. We maybe turn the heat down. We just make different choices. We might choose to build a house. We're going to build it more efficiently, build it to be more efficient. Maybe it's a bit smaller. We choose a more efficient vehicle. That's some of the ways. We can replace fossil fuel with zero carbon energy. So an electric car is a good example of that. We're going to run it on the Ontario grid, which is low carbon grid, and now your car is going to have very few emissions. Or possibly you heat your house with a heat pump. And so now you're heating your house with clean electricity and you reduce emissions that way. We can sequester carbon, and I'm not talking here about planting trees, although that's a great thing, and there's certainly lots of land in Ontario we can plant trees. This is more extracting it from the stacks, you know, at a large power plant, let's say, and compressing or liquefying the CO2 and putting it somewhere. Not a sustainable solution. It's going to work for a few years. It's also not proven yet to be economical at sort of the current energy prices. There's probably a place for decarbonization, but I have a feeling it's more than 10 years away. There's a lot of lower hanging fruit we can reduce emissions. You can't capture the tailpipe emissions from cars or trucks, though. There's no way to do that. So, you know, efficient or low carbon transportation, there's no sequestering of emissions from vehicles. It's just the technology doesn't exist. And we can reduce methane leaks. From landfills, but also from energy systems, refineries, gas pipelines, that kind of thing. So in Ontario, I'm going to make some assumptions. Broadly speaking, let's say we improve efficiency by 30% by 2050, somewhere in there. For replacing fossil fuels for transportation and heating, I think we need to set the goal of 100%. We should have all electric vehicles in 30 years, and we should have all electrically heated buildings. There's going to be a few that aren't there yet, and there'll be some specialized vehicles. But basically, we're going to replace all the cars by 2050. Nobody's going to be driving a 30-year-old car by 2050. So, you know, these goals are possible. I don't think there's much near-term sequestering in Ontario, so I'm not going to look at that in any detail. It might be a little bit of the solution later. Methane leaks, if we tightened up the methane, we can get about 4% of our greenhouse gas goal from reducing the methane leaks. So when we replace fossil fuels with some sort of clean energy or low greenhouse gas energy, I'll try to be specific on that, we've got transportation, buildings, including houses, and industry. So when we change to electric cars, they're way more efficient. A gasoline car engine's about 10 to 15% efficient at actually propelling the vehicle down the road. You put your hand by the exhaust, put your hand on the radiator, what do you feel? Heat, right? That's waste heat from the fuel. And so piston engines are very inefficient. EVs are way more efficient. So you get a lot more kilometers per unit of energy. So that's very good when we're switching to vehicles. I'm going to show you a little bit about EVs. I'm not going to dig in too deep, but a lot of work I've done shows EVs in the range of the low $40,000 range, which there are some now, have about a 5-year neutral cost against a car that would, let's say, cost $25,000 new. The fuel savings and the resale value and the lack of needing to do any maintenance gives about a 5-year neutral cost. But yes, you need the capital to buy the $40,000+ car. Natural gas heating systems, if you replace them by heat pumps, you also get a real energy boost. You're going to double or triple the heating energy you get for each unit of electricity you use. So heat pumps are great that way in terms of using electricity effectively to provide heat for space heating. Industrial processes, there's so many different types. Some are low temperature, maybe melting chocolate or something. A heat pump can do that, around 60, 70 degrees Celsius. Obviously, smelting metals and other industrial processes need higher temperatures. And electricity can do some of that. Biofuels could. Hydrogen is a potential there. You get into all sorts of complicated issues here around international trade and economics of various industries. So this is going to be a tricky area to do. But we can replace this energy with low or zero greenhouse gas energies. This is just sort of the range of vehicle emissions that we typically get. So in Ontario, if we use a battery-powered electric vehicle and we drive it on that battery for 20,000 kilometers using electricity in Ontario, you produce about 0.1 tons. So very small compared to even the hybrid car at 2 tons or the pickup truck at 8. And maybe a Tesla pickup truck will be a little more than this because it'll probably be a bit more electricity consuming, but somewhere in the less than 0.2 tons. Hybrid vehicle, plug-in hybrids where you're running partly on electricity, partly on gas, probably in the 1.8 to 2 and a bit. Again, just sort of assuming 20,000 kilometers a year, and I assumed that half the miles are on gas and half are on electricity. Then you get back to your regular gasoline technologies, and that's sort of where the 2 to the 8 is. So there's significant reductions possible if you go to the pure battery, or if you go to a plug-in hybrid and you plug it in a lot, you could get lower than these numbers. So that's one of the key directions we need to go. These are just some shots from the recent auto show in Toronto. There's electric cars everywhere there, and lots of stands had pictures. This is the Ivy charging network, which is going to be owned by Hydro One and the OPG. So the OPG is now getting into the electricity business for electric cars. These are the Petro-Canada chargers. This one's happened to be in Cobourg. Petro-Canada is I think Suncor has some stations in Alberta now, electric and Petro-Canada. So we're seeing oil companies make this switch as well. I think there are 96, maybe an EV owner here will correct me, but there's about 100 of these stations across Canada now, just with Petro-Canada, and many, many hundreds with other private firms. If we look at electric car sales worldwide, in 2018, the total electric car number was about 5 million worldwide, with a couple million in China. We've got about 138,000 in Canada as of the third quarter last year. And the International Energy Agency, which isn't known for being super progressive, they forecast, their recent report in the fall forecast 250 million vehicles on the road by 2030 that are electric. I think there's about 1.1 billion cars in the world. So they're looking at a 25% penetration by 2030. And that has all sorts of giant implications, of course, for oil prices and other stuff. Okay, and just really quickly on prices, this is just a chart that shows the MSRP of current crop of electric cars available in Canada before the $5,000 rebate. And this is the range as rated by Natural Resources Canada. And you see there's really 2 clusters of cars. There's these 200-kilometer cars in the sort of $40,000 plus or minus a few thousand. And then there's a 400-kilometer cluster of cars in the sort of $45,000 to near $55,000 level. There's some more expensive stuff out here, and there's a smaller two-seater car there. But that's just to give you sort of, an idea of the current crop of vehicles that's available out there. So any of these vehicles would be in that 0.1 to 0.12 tons of greenhouse gases per year if you drive them about 20,000 kilometers a year. Air source heat pumps. How many people here have an air source heat pump now? Holy cow. Wow, that's fantastic. And how many people put that in within the last 5 years? Okay, so that shows what's happening, right? There's this incredible shift. Nova Scotia is way ahead of us that way because they haven't had natural gas, so people have been putting in air source heat pumps for longer there, but they're coming on strong. I just renovated a house with my partner. It's on natural gas, but we needed a new furnace, so we put in a heat pump. The cost is almost the same as the new furnace. Can you hold the question till the end? Try to remember if that's okay. So this is going to be a big part of how we get to low greenhouse gas emissions. Yes, there's a capital cost barrier for lots of people, and how we're going to address the rural poor this way is an important issue. But carbon taxes, the tax bill financing, green bonds, there are policy techniques that have been used. If you put in a heat pump, your emissions for heating your house basically, again, go to a fraction of a ton. So if we take that internal combustion engine vehicle, we make it electric, we're about 0.12. If we take our house and we put it a heat pump, we're going to less than a ton per year, depending on the size and efficiency of our house. If we go from an omnivore to being a vegetarian, we'll go from 2 to 1 roughly. And if we choose not to fly, but maybe do something local, where we drive our electric car at some point, then your 10 to 22 tons, which was the previous sort of average Ontario person, is reduced to 1.5 to 2 tons. So that's your 90% reduction in that range. And those are all things that people can do today technically. Yes, affordability is an issue. I don't deny that. So that's, to me, very hopeful. The barrier is how do we finance, how do we create policies, how do we get to that point? But that, to me, is a very hopeful sign that today we can make these changes. So, vehicle, home heating, food, and air. Those are the big things in terms of home stuff. We can get major reductions. Capital cost is an issue, but in things like the electric car, the life cycle costs will be equal, and I think very soon, maybe within a few years, as electric car prices come down, it will just be obvious that an electric car is a lower cost vehicle to drive. And one of the big things that already came up was if you just consume less, you have fewer emissions. And I don't know if any of you saw the article, but in China, some satellite imagery from the last few weeks has showed that, and not that I want coronavirus to be the way that we reduce greenhouse gases, but greenhouse gases in China have gone down 25% because people are just doing less and factories are not at full production. Air traffic is down hugely. And so there's definitely, part of it is the fever that we live at in terms of consuming. If we consume less, we're going to emit less. But what I proposed doesn't really, these things don't mean we're living all that differently. Maybe our electric car can't go quite as far as easily, but the rest doesn't make much difference to our lifestyle. Okay, so let's go on and look at the whole province. If we, electrify a lot of what's currently producing greenhouse gases, what does it look like? This is the turn of the century, 1906, when a lot of Ontario did not have electricity still, and there was a huge wave of electrification, and so big projects were done, and these are the tunnels being built in Niagara Falls that were going to carry water to the early electrical generating station. So these are major capital projects that the province took on to electrify itself. And this is a graph, and I know you can't read the lines down here, but this is 1911, 12, 13, 14, and this was a Toronto Hydroelectric report from 1914, and this was the growth rate of houses connected to the electricity system. And this graph over here, unfortunately, didn't have the units, it's just ratios, but these were the total load electrically that the grid was carrying, and it basically had tripled in 4 years. So, very significant growth can be achieved. And I consider ourselves to be in a similar state to that early 1900s. Some of you have probably seen the talk by Tony Seba about electric cars. Anybody seen the Tony Seba talk? He looks at electric car adoption, and it's very similar to electricity adoption in the turn of the century in terms of the disruptiveness that could potentially occur. So basically, I think the way that we're going to end up going is electrifying. Our heating, our transportation, our industrial, our commercial activities are broadly going to be electrified. And what does that mean? What do we electrify? How much electricity does it require? That's a big one. So I'm just going to ask, so if we electrify all the vehicles in Ontario and we electrify all of the building heating and we electrify 75% of our industry, how many people think it will take 10 times as much electricity? How many people, that was nobody, by the way. How many people think it'll take 5 times as much electricity? You got a couple. How many people think it'll take 2 times? Okay. No, you guys have been reading, you've been reading the reports. Most of the studies that I've been, and there aren't a lot on this yet, there's just a handful that are in the Canadian context, but it's going to look about doubling. So let's take a look at what that means. It's about a doubling of our electricity consumption. So these are my caveats for my analysis, okay? Because this is complicated stuff, and I did not have $1 million budget or a team of consultants, but I did create a very large spreadsheet, and for the last year I've been tweaking it and adjusting it and having fun with it. I'm just shooting for an 80% reduction by 2050. So agriculture, the oil production in some of the facilities, I'm just not addressing that in my analysis. I just wanted to look at, broadly speaking, what would happen. So demand's been flat for about a decade for electricity, and there isn't any indication that would really change if we weren't going to go to electric cars and electric heating. Efficiency, despite population growth in Ontario, efficiency improvements have basically levelized the growth in consumption for the last nearly 20 years. And my assumption is that renewable electricity is the new supply. Some would come from Quebec, hydro imports, but obviously they'd be happy to sell it to the Americans as well at maybe a higher price, so that's an issue. Storage cost, meaning batteries, are greatly reduced, and that's partly the electric car revolution, but those batteries can be on the grid. I'm not proposing there are any new dams in Ontario, so no big political issues around dams. No new nuclear. I'm 100% confident it's too expensive, and if they ever go out for quotes, it will look too expensive. We'll use some natural gas for peaking, and at some point we might want to change that natural gas to hydrogen or biofuels for winter, night, cold, peak loads. But they're a relatively small part of the overall annual energy consumption, so they don't carry a huge greenhouse gas penalty. And we're going to have to expand the grid, of course, in capacity to carry this extra power, so there's going to be a cost that has to be built in. It's not going to come free, but we're going to save billions on gasoline and diesel. So, we're saving, and natural gas. So there is a cost reduction on the fossil fuel side. So let's take a look at what we've got here. Right now, in Ontario, we consume 22 billion liters of gas and diesel each year, and about 32 billion cubic meters of natural gas. That's for everything. Cars, buildings, everything. What amount of electricity would be required to replace all that energy? We have to look at the efficiency it gets used at. Electric cars use electricity much more efficiently than gasoline. So you don't have to, it's not a one-to-one comparison. The energy in the gasoline doesn't have to exactly match the electricity. You actually need far less electricity than you did gasoline energy. And then I'm going to compare that result to what we're currently producing in Ontario and see what kind of trouble we're in. And as I said, most of the studies are showing that it's about double, and I've seen them now for all across Canada, for Nova Scotia, and it indicates it's about double. So right now we use about 137 terawatt hours. So these are how utility people talk, because once you're big, you need these kind of simplifications, because that's a lot of kilowatt hours, as you can see. So if we electrify all transport, and this includes all freight trucks, pickup trucks, basically the same vehicle mix we have today, but running on electricity. So it doesn't mean we're all driving tiny cars. That would be great, but I don't think that's how it's going to go. Basically, we need 45. What was the total for Ontario? 137, okay? If we put heat pumps for all of our building heating needs that are currently met by natural gas and oil, we'd need about 41 terawatt hours of electrical energy. And if we do about 75% of industry with a combination of heat pumps, we would need about 80 terawatt hours. So the industry is a big one because a lot of the energy used there, it's not as easy to get that heat as efficiently as a heat pump would use. So some of it has to be used sort of a 1-to-1 ratio for energy like steel making or something like that. So it remains a biggie in terms of changing. So that's an additional 166. So just looking at back to the pie chart, there's our transportation. Oh, I guess the colors changed, sorry about that. 45 terawatt hours for our transportation, 80 terawatt hours for our heavy and light industry, and another 41 for our building heating. And then if we had an ambitious plan and actually properly dealt with our organic waste and capped dumps or made sure it didn't get into landfills in the beginning, we could knock out another 6 megatons, and that's 81%. Okay? And we didn't touch agriculture. We haven't touched the upstream fossil fuel emissions. We haven't touched construction waste. There's a few little slices of the pie there we haven't messed with yet. So that's what we need, double plus a bit. So you think, wow, that's really bad news. Double is really big. But look at this graph. This is how many terawatt hours we've used in Ontario since 1970 by year. It should probably be a bar graph for those of you that are technically minded rather than a line chart. But each of these points by the year represents the terawatt hours for that year. We were at 62 in 1970, and by the year 1990, we were at 140. That was a 225% increase in 20 years. That's when we built the nuclear system. We went into debt, too, to build them, of course. So it didn't come at zero cost, but certainly in terms of what we can do, technically, we have doubled the capacity of the grid in less than the 30-year window we have to 2050. So this is very doable from a technical standpoint. So the grid can change. And so at this point in time, we've got technologies like batteries and the Internet of Things, digital control. Yes, those introduce security risks to the operation of the grid, but energy storage would have to be part of a future grid, for sure. Millions of electric vehicles are going to be connected to that grid, and they can both take energy from the grid. They can also return it back to the grid under what's been termed vehicle to grid, V2G. It's being demonstrated in some places in the world. It isn't massively adopted yet, but it's totally technically doable, and we can program our cars to charge at specific times at specific rates, and we can program them, or the utility could potentially program them to grab power back from those cars at certain times as well. So if you imagine 1 million vehicles that each have a 60 kilowatt hour battery, that's a lot of energy storage. And it's great for the utilities because the customer's actually paid for the storage, not the utility. You buy the car, you have bought the storage that the utility is going to use. So there's some really interesting economics to having electric cars be part of the grid. Thermal mass can be used in the wintertime. If you just put hot water in tanks or cold water in tanks, you can take off the peaks of heating and cooling, and that's done in many places around the world, especially for air conditioning loads in the southern states, where they buy cheap electricity at night, chill a great big tank, and then use that cold water during the day to cool the building. But we can do the opposite here. And then biofuels and hydrogen. Hydrogen obviously doesn't occur naturally in the gaseous state in any quantity. So we need to make it, and we'd have to make it from a low carbon energy source. If we crack it out of natural gas and put the CO2 in from the natural gas, that's not getting us there. So we've got to make our hydrogen. But it will be a relatively small percentage of the overall energy mix. So I'm going to propose that the 166 terawatt hours comes from solar and wind. Okay? Storage being an issue for sure in low wind and low conditions, and that's why we need storage. And then demand management as well, and that's going to be through the internet basically, with a variety of algorithms and protocols for how that gets done. And we already have that. There's already all sorts of programs industrial consumers can sign up for where they get cost benefits from having the grid tell them when or when not to use certain amounts of equipment. That can be done. So just in terms of this much renewable energy, these are some frame of reference numbers. Greater Toronto is about 7,100 kilometers of buildings, roads, parking lots, and some green space. The Alberta high-level fire, many of you will remember that from the past summer, burned 2,700 kilometers of forest, 2,700 square kilometers of forest. The Wolf Island Wind Farm, how many have seen that? Wolf Island Wind Farm. So I think it's got, is it 86 machines? I may be a little off on that. Produces about 0.6 terawatt hours a year. So remember, we need another 166 to do everything. So if we say we're going to make half of our electricity with wind farms, we need 83 terawatt hours. So we're going to need a lot more wind turbines. So I thought, well, what's that going to look like? The photovoltaics would require a land area, and this is putting them in rows like you would have seen in solar farms. And I'm not proposing that they all go in this location in Ontario. Maybe that would be great for local jobs, but there'd probably be some very unhappy people too. But overall, we need about 900 square kilometers of photovoltaic farms. Okay, so it's not insignificant, but it would also be widely distributed. And this is where fallow farmland and unused land is potentially part of what we would have to do, and there will be issues over that. My point of view is, what's our other option? What is our other option than to do something like this? If we don't change, we're in big trouble, so that we have to find a way to make these changes. Whoops, we need about 160 wind farms, the size of Wolf Island, to make this energy. So if we want to consume at the level that we are, if we want to have our houses at the same size, we want to drive our cars the same distance, this is the kind of decision that we're going to have to make, or we somehow conserve and use less energy. But we're still going to have to electrify to reduce greenhouse gases, and it means some sort of impact this way. So just in terms of the past, we have already installed 11.7 terawatt hours of wind and solar in Ontario. So we're already at a sixth of the solar that we need in terms of supply. Sorry, we're already at 11.7 out of 166 of wind and solar. Last year, wind and solar supplied about 8.6% of all the electricity we consumed in Ontario. Okay, so lots of big growth would be required there for sure to get to the 166. Right now, 75% of the vehicles in Ontario are replaced every decade. So in terms of putting in programs to get to new, cleaner fleet, if we do that soon, within a couple decades, basically all our vehicles would be new. The people aren't driving around in 20-year-old cars. The vast majority aren't. Some of us might have them, but they're really a very small percentage. So the bulk of vehicles, if we get programs in place which get cleaner vehicles into the hands of people, low carbon vehicles, then within a couple decades we've changed. Most heating systems in houses probably last 20 to 30 years, somewhere in that range, maybe some a little shorter, some a little longer. But again, in terms of the 2050 window, we're basically going to be replacing all of these systems. So that's why we need to start now with programs that get heat pumps and efficiency into houses in a scale, like Gord was mentioning, the 7.5% a year that we have to reduce our emissions. We need to be looking at retrofitting 5 to 10% of houses every year or two need to be retrofitted and taken to low carbon, very low carbon housing and commercial buildings too. In terms of transport, we spent about $26 billion. So these are what's it going to cost? What are the dollars attached to this? Got about 10 more minutes here, and we'll go to questions. So we spend about $26 billion in Ontario on gasoline and diesel each year. That same fleet as an electric fleet would cost us $7 billion at 16 cents a kilowatt hour, which is around what many people are paying on average for electricity. So it's a $19 billion cost reduction in the energy to operate our vehicles. We do lose $7 billion in taxes on that gasoline and diesel, so we need to make that up. How that gets made up, whether it gets tacked on to vehicle operating cost or whether it's a new revenue stream, I mean, those are where we need to have some serious policy discussions. Should electric vehicle owners be paying an equivalent fuel tax? Right now, we don't. So let's say it costs, even if we build it all into the vehicle operating, it would still cost us a lot less. So we're going to save, in the order of $10 billion running our fleet on electricity at today's electricity prices, realizing that can change. Okay, so there's probably not a cost penalty for that. Even if electricity was 25 cents, we're still going to have reduced costs. And how many people here have electric cars? And I'm sure you've all noticed how little it costs to run them. It just costs so little to run an electric car. You really don't think about it. I'm absolutely convinced I spend twice as much on beer per year now than I do on electricity. And I don't drink and drive. It's literally $400 or $500 a year to run a car on electricity. So it's just very inexpensive. And no oil changes, so there's other savings too. In buildings and industry, right now we spend about $8 billion at 25 cents a meter cube. Prices vary a lot between residential and commercial and institutional, so it's a little hard to get an exact number, but it's in that range. We spend about $8 billion. Natural gas is super cheap as an energy source. It's super cheap per unit of energy. It's one of the cheapest forms of energy. If we convert all those buildings to heat pumps, it'll cost us about $6.5 billion to run the heat pumps, making the same heat as the buildings need now. So there's an operating cost, sort of neutralness, but there is a capital cost impact to get there for sure. We got to retrofit all these buildings. More problematic is industry. The energy required for industry, given it won't be as efficient, if we use electricity directly for industry, it would cost about 12.7. So we'd be going from $8 billion of natural gas to nearly $20 billion of electricity to do all the building heating and to run all of industry. So this is where I think that the industrial energy we need to look seriously at biofuels and hydrogen as an option for that. And that's going to require, significant resource. We're also competing internationally in industry, so what other countries do and what their energy costs are impact what our options are for this. So this is where, public policy and commercial competitiveness need to be integrated into resolving how to get industrial emissions down to the levels. But we can still take out a lot of carbon with, our buildings and our transportation. So what would it cost if we, at today's prices with wind and PV, wind and photovoltaics, to make that terawatt hours? Be about $124 billion of capital cost investment today to make that energy from wind and solar. That's today's prices. Solar's coming down quickly, still coming down relatively quickly. Over 30 years, it would represent in today's dollars an investment. Around $4 billion a year would build all that energy generation technology. Relative expenditures, we're spending $34 billion on fossil fuels. Ontario's GDP is about $854 billion. The cell phone market in Ontario, not just buying the phones, but your monthly fees, is about $10 billion a year. So the transition to a complete wind and PV, zero carbon for transportation and building, is somewhere less than the cost of our cell phones over the next 30 years. Bruce and Darlington were $26 billion to refurbish. Darlington's still under refurbishment. The IESO has put $70 billion, that's the electricity system operator in Ontario. In the last 20 years, roughly, they've spent $70 billion retrofitting the grid. So these kind of $100 billion projects over 10 or 20 years are the normal for grid development. There's nothing unusual about, the $100 billion kind of price tag. Oh, sorry, I got that twice there. Oops. If all that energy was replaced with the electricity, our electricity bill would be about $27 billion. It's roughly comparable. I'm not going to hold my my numbers are not that accurate, I can assure you. But it's somewhere in the same sort of overall cost range per year of electricity to replace all that fossil fuel. But here is some of the benefits. Every house is going to have to be converted to a heat pump. That's a lot of jobs, and those jobs are in Ontario, and they're local jobs in every community. You know, the people that put in heat pumps in Perth aren't coming from Nova Scotia or overseas necessarily. They're local people who live in the community. There'd be a lot in large urban areas where vehicle emissions cause many, many premature deaths from the sub 2.5 particulates. We're going to see some studies I've seen indicate billions, literally billions of dollars less in long-term health care because of reduced urban pollution from electric cars. People, once we have converted to heat pumps, people that are living rurally won't have the high oil and propane costs that they do today. And lower vehicle costs, $500 a year for fuel versus sort of $2,000 now for a relatively efficient vehicle. So those are some of the benefits. We talk about the issue of just transition, because this is a transition where jobs will be gained and jobs will be lost. So we're going to spend billions on building renovations to be more efficient and heat pumps. Lots of widely distributed jobs in both urban and rural areas. Existing fossil fuel distribution is going to be hit hard. There's going to be a lot of gas stations that won't be required. Fuel oil delivery companies will no longer be necessary. Mechanics whose expertise is maintaining piston engines and fuel injection and all that stuff, they're not going to be needed as much. So we need to anticipate these transitions and train people. And having worked at the college in Kingston for 15 years, I mean, that's one of the great things that colleges do in Ontario is anticipate these kinds of technical changes and institute training programs for them. So for instance, training people to repair electric cars in the automotive programs. You don't need any supervision when you're plugging in your electric car to charge it. You don't need an attendant to help you. So, you know, the whole refueling industry changes. The whole re-energizing industry changes when you have electric cars. We also don't make any electric cars in Ontario. So what's going to happen? Are we going to make electric cars in Ontario? Does the government have a plan for that? We do make hybrid vehicles in 2 locations, but we don't make any pure electric cars. So our automotive industry, you know, how do we make sure that it's part of this transition? Some other important issues, fuel tax, I talked about that. Sources of capital. Carbon pricing to me is an obvious one, and I'm not quite sure why the federal government decided to return the carbon price. I think it would make more sense to take that carbon cash flow and use it to create these changes that we need. We can do it through taxes, other taxes. Green bonds are one way. There's also adaptation to climate change. So if we spend too much on adaptation and not enough on mitigation, or vice versa, that's not good either. So we need to mitigate, which is the reduction part of greenhouse gases, but there's also going to be issues around weather changes and disease vectors that we also need to spend money on. So that hasn't been very well resolved at all yet. Then there'll be federal and international progress that influences what we can do provincially. Obviously, our industry can't just march off on a hydrogen path if the rest of the world doesn't. And so there's issues about who moves in lockstep with whom around the overall changes required. And I think the past projects on photovoltaics and wind showed that there needed to be a lot more community engagement. So if you're going to start putting in that amount of photovoltaics and wind, you need a lot of community talking and discussion about benefits, issues, costs, the negative aspects. That has to be something that communities are deeply engaged with. So moving forward, that's pretty much the end. And I just got one quote here that is my own and just reflects what I think is going to happen as this greenhouse gas, the need to reduce greenhouse gases gets more and more critical. This is what I think has to happen. Oh, sorry, didn't quite get that right. These are steps towards the end. So one is we need a provincial government that actually seriously takes the responsibility for going in this direction. We don't have that right now. I think that the way to do that, when we do have government leaders who can make that decision, is that we need an all-party committee, and that committee needs to look exactly what I'm talking about here, but in a much more detailed, much more in-depth way with lots of economists giving input. We need to look at a variety of paths that get us to this option. Electric cars are one, heat pumps are one, but there's other smaller aspects of this that we need to look at. And there was actually an all-party committee under the Harper government. They actually had a climate change all-party committee. Very few of us probably even know that. And they were trying to look at some of this stuff, but there wasn't enough horsepower behind the activity. But it's not a new idea. We need to look at the job creation and the job loss, and what are the just transition issues as we go to this 2050 target. And I just mentioned some of the job issues, but there will be many others, I'm sure. And that will evolve as costs change and as international agreements change, and as we learn more about the impact of climate change, we will have to keep updating that and revising it to reflect the technical and economic and international and local political issues. Then we've got to create the legislation to make it happen. I used to think that everybody just needed to learn more about the problem and make decisions like, turning your heat down and getting a more efficient house and getting a more efficient car. And I've really come around to realizing that just like unleaded gasoline and the fact that all our cars have catalytic converters, we didn't ask for that individually. Large forces drove us in those directions. Why do we have an electrical code for building our houses? So they don't burn down. There's all sorts of legislation out there that is ultimately designed to, move us in safety or in health forward. And so, we need legislation to allow people to get electric cars at affordable rates. We need legislation that creates the infrastructure to put in literally millions of heat pumps. Okay, so here's the statement that I was going to talk about. Okay, thank you very much. Public transit is a huge part of that. So locomotives that run on electricity, well, they wouldn't be called locomotives anymore. Mass transit is a huge part of that for sure. I think there is a very complex thing happening with the possibility of self-driving cars and mass transit. And we're going to need legislation around how that unfolds, because it's going to be very tempting for people to buy self-driving cars and not take transit, because it's probably going to be quite cost effective in 10 or 15 years to get an economical self-driving car, and you can work while you go somewhere, or you can sleep while you go somewhere, and a lot of people are going to want that overriding in a subway car. So I think there's some really important work to be done as soon as possible to define how we want that to unfold. There's some really complicated issues there that are going to come up when self-driving cars are successfully commercialized. In the back in the green? Electric tractors, for agriculture in Ontario are probably not just around the corner. That is not a 5-year possibility. They need a lot of power because of the kind of job they do. But electrified ships, there are already some, for large transoceanic, there are some hybrid diesel ship designs being looked at now. They're actually being built. There's some being built. I'm not intimately familiar with the technology, but there are some being built. So they seem to be opening up a commercially viable window to use less fuel for large freight transport. Dump trucks, mining vehicles, many mining vehicles are already electrified, ones that work underground, because in coal mines, combustion engines are not a great idea with methane. So there are already quite a few electrified, and emissions underground as well, the resultant emissions. Again, if you look at the numbers, it's passenger transport in the transportation world and freight trucks that are the bulk of the emissions. So, tractors and local dump trucks hauling gravel can probably be part of our mix for quite a while. They're not the bulk of the emissions, and that's why I was talking about like 80%. There's still 10 or 20% there that's happening. How do we address that? how easy will it be to convert all those dump trucks to some other technology? I think that's something we can look at seriously. Even in 10 years, it's okay to look at that. As long as in the meantime, we're converting all the passenger cars and houses. That'll get us a long way towards that 2030 requirement. I think someone over here was next, maybe with the glasses. I mean, it's a great point, and I guess the way I've developed my thinking on this is that to not go this way is much worse for biodiversity. If we don't address climate change, we destroy habitats at a scale that is just unimaginable. And so yes, there's going to be a cost to whatever energy system we build. Is going to have a biodiversity impact. It's going to have an impact on birds, on land where we put solar photovoltaics. And as a society, if we could agree on using less energy, then that becomes less of a demand, less of an impact, because we need less equipment. But to me, I've found that the idea that we can, as a society, use a lot less, I don't see it happening. The momentum for the lifestyles that most of us expect, it really hasn't evolved hugely in the last 30 years. We're more efficient, but we really aren't living in much smaller houses. We aren't really driving much differently. And so the way I look at it is there's going to be an impact. And what's the least impact? Right. Not that there's no impact.
Right. As you've shown, electrification is going to increase. I guess kind of what
Yeah, and that's, I think, something that that's the $1 million study that needs to be done, is to look at where are the least impactful places in Ontario to install these systems? What would cause the least habitat destruction and the least possibility of extirpation of certain species? And again, I go back to the option being doing nothing is worse for biodiversity. So how do we move forward in the least impactful way is worthy of a lot of thinking, but we have to do it pretty quickly. We don't have 20 years to mess around with this anymore. I'm not really sure who is next. I'm sort of losing Peter? No, that's a great question. There's probably enough roof area to do all the solar, almost. The problem is the roof-mounted systems are not cost-effective, not nearly as cost-effective on a large scale. So if you're looking at putting 100 megawatt wind farm in, which is several hundred acres, the cost per kilowatt hour to make the electricity from that wind farm is about a quarter to a third the cost of it being rooftop systems. So again, it becomes one of these decision points about, do we want to use up land and have cheap electricity, or are we okay paying 2 or 3 times for our electricity but having it be on roofs? I mean, a lot of industrial buildings have large roofs, and we could obviously put many hundreds, probably thousands of megawatts on industrial buildings, but we would also need to use the roofs on a lot of smaller places, and the cost effectiveness is not as good, and we know how political electricity prices are. So again, it's very difficult to push for electricity systems that would double the kilowatt hour cost. And so the cheap electricity is going to come from ground-based, large-scale photovoltaic systems if we want it to be low cost. The woman in the black hat at the back there, sorry. Yeah, there are 2 paths with hydrogen for vehicles. One is you can burn hydrogen in a conventional spark ignition engine. It's been done many times, and there are many places in the world where large engines run on natural gas, but they can also run on hydrogen as a fuel. They still have emissions issues, nitrogen oxide in particular, but if you run it on hydrogen, you get at least no CO2, you just get the nitrous oxides. In terms of fuel cells running on hydrogen, I think we're seeing some penetration into the market now. I saw an article just yesterday that a train in Europe is being it's being pilot run, it's actually constructed, it's running on hydrogen-based fuel cells. One of the issues with hydrogen is that there is no free hydrogen available out there. We have to make it, and you need to make it with a low greenhouse gas impact, obviously, so it has to be made with an electrification technology that has a low greenhouse gas impact. So that could be nuclear. In the case in Ontario right now, I'm not a big fan of expanding nuclear, but if you make hydrogen from nuclear and then use it to run a fuel cell tractor, theoretically that's a low carbon. But you could also make that hydrogen from photovoltaics or wind or hydroelectric power. Right now, that path is not a very cost-effective path, right? Because you got to make the electricity, and then you got to make the hydrogen, and then you got to store and ship the hydrogen, and then you got to burn it in a fuel cell that maybe works at 60% efficiency, so you're not even getting a lot of the invested energy back, and the fuel cell itself is not a cheap capital cost item. So for things like tractors, what will win out there? I think what would make sense is biofuels. Use a liquid biofuel and run your conventional tractor. They last for a long time, the investment's made there. But biofuels are also more expensive right now than conventional fuels. So again, if you want to take emissions out of the millions of tractors that must operate in North America, you need to have some sort of support for people to use those lower carbon fuels, because they're not going to be competitive against gasoline or diesel at today's pricing structures. And I'll just add one complicated thing that's going to happen, and we're seeing it sort of this week as global energy consumption goes down, is the price of oil is falling. And if we successfully address climate change, it's going to fall a lot more. And so things like tractors that might run on gasoline still, they're going to get cheaper to operate as fuel costs fall. So are cars, the gasoline cars. So we're going to get into this weird state where conventional fuel prices start to come down as we actually succeed with climate change, and it makes the economics of some of the transitions even more difficult. But that's where carbon taxes and other legislation can help. In the back in the blue, heat pump technology comes in two types, ground source based, where you're basically, in the winter, you're cooling the ground. In the summer, if you have air conditioning, you're actually heating the ground. And air source heat pumps in the winter actually take the winter air and chill it even further. And that energy that's removed from the air ends up appearing as heat in the house due to the refrigerant cycle of the heat pump. How the heat gets into the house can be a variety of ways. It can come in from the heat pump as refrigerant, hot refrigerant, that the heat is taken out of, and that refrigerant is then returned in a cooler state to be resupplied with more heat by the heat pump. Or it can be a liquid water or glycol antifreeze interface. In reports that I've been reading that look at heat pump technologies, they're estimating by 2050 some of the heat pumps will be operating, right now they're 200 to 300% depending on the temperature, so you're getting 2 or 3 units of heat for every unit of electricity you put in. But new heat pump technologies are evolving, and design refinements, and projections out to 2050 are saying there'll actually be 4 to 5 units of heat for every unit of energy you put in. I didn't use that number, and I used the current technology. And the way that that's going to happen is heat pumps are going to use, and they're already available from a number of Japanese manufacturers. They're using, it's sort of weird, they're using CO2 as the coolant. And they actually use CO2 in what's called a supercritical state. It's highly compressed at several thousand PSI. And those heat pumps operate at much higher efficiencies than our current generation of HFC-based heat pumps. And so at some point, the heat pump market is going to shift to those higher efficiency heat pumps. They're more expensive right now. Again, it's an economic question. But when we make millions of them, the cost will come down, and the efficiency gains will be important to have. Does that answer your question? So many people in the audience about that. What about when it's really, really cold, the efficiency isn't as good? And that is true. When it's really, really cold, air source heat pumps, it depends on the technology, but by -17 to -25 Celsius, basically it's like running a pure electric heater. You don't get the huge efficiency gains. The geothermal systems are better that way, that the ground is always at sort of 6 or 7 or 8 degrees Celsius. So they continue to operate at a plus 100% level. The difference, the challenge is the ground source is so much more expensive to install. So the capital cost of the ground source heat pumps is why the market's going to air source with pure electric as a backup. And the studies that I've been looking at, one of them just in the last couple of weeks from ICF for actually Canadian Gas Association, they looked at heat pumps, air source heat pumps, because of the lowest capital cost, but they acknowledge that they're not going to serve about 1% to 2% of the heating needs in Canada, because those heating needs are below -25. But most of these houses in urban areas that already have natural gas could continue to have natural gas and use a tiny bit in the winter. There'd be a greenhouse gas impact, but all the infrastructure still exists to service those houses with natural gas. Yes, it will cost money to maintain that infrastructure, but one of the paths is using a bit of natural gas and using the bulk of electricity and air source heat pumps, and that's what the industry is sort of seeing the evolution as right now. Yes, geothermal can be better in the summer too, but the bulk of our greenhouse gas emissions are associated with the heating season, because once you have clean electricity, the air conditioning load is basically, well, I should say, once you have low greenhouse gas electricity, the air conditioning loads actually have near zero greenhouse gas impact. Yes, in the very back. So manufacturing liquid fuels from artificial photosynthesis. Yeah, I am not up to speed on that as a technology development, but having been in the fuel cell and the battery business for 20 years before I was at the college, what I think about technologies like that is, if they're not commercialized right now, they're probably at least 10 years away from commercialization. And so they may be part of the solution at some point, but they're not part of the early transition that we need to be making right now. So it may be that, before 2050, solid state batteries, genetic engineering of plants, biofuel production through genetic engineering, and I'm not saying that I want any of those things, but those things may be possibilities that take us forward. The one interesting thing about photosynthesis is it's actually very inefficient. Only about 2 to 3% of the sunlight landing on a plant ends up stored as energy in cellulose. Photovoltaic modules now are 15 to 20% efficient. So in terms of unit area of coverage, now you'd be covered with the land with plants versus photovoltaic modules, but there are some efficiency issues, and that impacts the cost of doing those kinds of things. But I think biofuels are something we need to stay on top of, and we need to find ways to sustainably, environmentally create biofuels, because they're going to fill some of the need for these high temperature combustion applications and some of the technologies that maybe aren't going to change quickly, like tractors, which are a huge capital investment and maybe last 30 or 40 years. Converting those to biofuels would make a lot of sense, and so biofuels become part of a logical stream forward. But exactly where they come from, there's many technologies that are emerging for biofuel production, so I can't comment on what I think will work there. Yeah. Is that good? We're good?
Thank you very much.
Okay.